Hello, I am Shiyu, 26 years old, and from the big QTQ team. I was born in Yunnan, China, and have just finished my master's degree in organic and molecular electronics in Dresden. Now I am doing my PhD in physics at Julius Maximilians University of Würzburg, working on light-matter interaction. Via the app QTQ, you again sent us exciting bonus questions. Some questions even made our team sweat. Today we are talking about photonics, the use of optical technologies and light signals, and why those cute little particles of light, the photons, are shaping our present and future.
Why is there nothing faster than light? Asks 17-year-old Knut from Hamburg, Germany.
Unfortunately, we cannot answer this difficult question at the speed of light, dear Knut, so we'll have to go a bit further. Let's start very basic.
How fast is light actually?
Light is a jack of all trades. It spreads not only in air or glass, but even in the absolute nothing. This nothing is called vacuum and exists, for example, in outer space. Light therefore does not need any material to carry it, unlike sound, which does not travel in vacuum, which is why it is completely silent in space. Light, however, is super fast in this nothingness and moves in space at almost 300,000 kilometers per second. By the way, radio waves or laser beams are just as fast, but nothing in our universe moves faster. Light can circle our Earth 7 times in just 1 second. Impressive, isn't it? You can see how fast it is every day when you turn on a lamp. Then the beam of light flees through the air from the lamp to your eye, almost as fast as in space. You see it immediately.
And why is light the record holder in terms of speed?
The fact that nothing is faster than light has to do with Albert Einstein. You met this Nobel Prize winner in the game QTQ and can also read about him in the Kittypedia. In his special theory of relativity, Einstein dealt with the motion of bodies in space and time and discovered that there is a maximum speed. But only tiny particles without mass, like light particles, photons, reach this insane speed, and only in the vacuum of space. Nothing has been discovered yet which travels faster in vacuum.
Does light always travel at the speed of light?
This will confuse you, perhaps, but light only reaches its superspeed in vacuum. It can also move slower. In water, for example, it only reaches about 75% of its maximum speed, but that is still 225,000 kilometers per second. The ratio of the speed of light in vacuum to the reduced speed in water, glass, air, or other media is called the refractive index. In water, this index is about 1.3. This means that light is sometimes overtaken by superfast cosmic particles in the Earth's atmosphere, for example. Faster than light is thus quite possible, but there is nothing that trumps the speed of light in vacuum. By the way, decelerated light can be controlled today, and maybe the computers of the future will work with light.
In which medium does light behave the weirdest? 16-year-old Matteo from Colombia wants to know.
You just heard something about the refractive index. This tells you how much faster light travels in the vacuum of outer space compared to other media such as air or water. But it gets particularly interesting when the light changes medium, from air to water, for example. Then it changes not only its speed, but also its direction of motion. In physics, this is called refraction, and the associated optical effect also looks like this. You've probably noticed the apparent bend of a straw in a glass of water, but the refractive index even makes stealth possible.
Stealth like in fantasy stories, does that already exist?
Well, first prototypes. The secret is a special non-uniform refractive index. In our laboratories, we can now artificially produce metamaterials with this uneven refractive index.
What's the point?
These specially made metamaterials behave quite differently from the way things otherwise behave in nature. To do this, The refractive index is precisely tailored by us researchers when designing these materials, so that it is more convenient for light to travel around the material instead of being refracted or reflected by it. The object thus becomes invisible by redirecting light. Back in 2015, the University of California in the US developed an ultra-thin cloaking device that makes tiny objects disappear. So, dear Matteo, in a nutshell, light behaves most strangely in tailor-made metamaterials.
What is a photon and what do you need it for? Asks Thomas, 15, from Columbia.
The term photon is derived from the Greek word phos for light and stands for the teeny tiny particles or quanta of light. As energy packets, photons form the building blocks of electromagnetic radiation. They behave like waves and particles at the same time. This wave-particle duality is one of the fundamental concepts in quantum physics. If you want to know more about it, feel free to read up on it in the Wikipedia.
How did they discover photons?
At the end of the 19th century, it was thought that optics, light, and its laws were completely understood. But there was one exception. One could not explain the solar spectrum.
What is the solar spectrum?
The sun emits light in many colors of different intensity, from red to yellow and green to blue. So the solar spectrum describes how much light the sun emits in each color and range. All colors of this spectrum together result in white light for our eye. In addition to visible light, the sun emits other types of light. Light with higher energy, the ultraviolet or UV light. Too much of it causes sunburn, so we protect ourselves against it with sunscreen. And light with lower energy, the infrared light. You feel this heat radiation as solar heat on your skin. UV and infrared light are invisible to us humans.
And how can we explain the solar spectrum now?
The solar spectrum can be measured, but why it is structured exactly in this way and why certain colors are emitted more strongly than others could not be described with the laws of classical physics in the late 19th century. Because according to them, there would be an ultraviolet catastrophe. Sounds terrible, doesn't it? It would be, because then the sun would radiate infinitely much light with infinitely much energy every second. We could burn in this extreme high-energy UV radiation. This, therefore, cannot be the case at all.
The solution came with the quantum physics.
The ingenious physicist Max Planck found it more than 100 years ago. Today, important research institutes are named after him. Max Planck calculated back and forth. Then he had a flash of inspiration. He assumed that light is not emitted evenly and without interruption, thus continuously, as it should have been according to the wave model of classical physics.
Planck found that the sun instead emits its light as tiny packets of energy. A light beam is therefore not continuous as it appears to us, but has constant small interruptions. One says the light is quantized.
And here, the circle closes to the beginning of this answer. According to Planck, light consists of tiny particles, the aforementioned energy packets, and the tiny light particles are called, surprise, surprise, photons.
And what are photons needed for?
After Max Planck clarified the wave-particle properties of sunlight and described photons, the research of light, photonics, took off. Photons are the basis for many modern products. Just look around your home. Examples include light-emitting diodes in lamps, screens and displays, solar panels, and last but not least, lasers.
A laser brings a large amount of energy to a single point. Single photons are generated and rapidly multiplied by mirrors and special materials. This results in a huge number of identical photons producing bright monochromatic light, pure quantum physics.
Laser technology is used in printers and headlights, in welding, and in medical treatment and surgery. By the way, Albert Einstein described the principle of the laser as early as 1917. The first functioning devices have been around since the 1960s. But photonics promises so much more, dear Thomas, not only through the bundling of light energy as in lasers, but also through the speed of light. Even today, telephone calls and data on the internet are transmitted as light passes via fine glass fibers. We live in the technological age of the photon, the century of photonics.
8-year-old Mala from Dresden has a really cool question. How hot is the sun, how cold is the moon, and how long are the sun's rays?
How hot is the sun? It depends entirely on where we measure the temperature. It is hot everywhere, but while it's still comparatively cool on the surface at about 6,000 degrees Celsius, inside it's up to 15 million degrees Celsius. And the moon? Because it has no protective atmosphere like the Earth, the temperatures on its surface fluctuate extremely between day and night. When the sun is shining, it can reach 130 degrees Celsius. In the dark, it gets icy, down to minus 160 degrees Celsius. The length of the sun's rays varies and describes the path of light, or more precisely of a photon, from the sun to an object on which it strikes. From the sun to the Earth, that's about 150 million kilometers. The light travels this distance in space in about 8 minutes at the speed of light. To Jupiter, it takes almost 45 minutes. And now have fun with ct.qmat and see you in the next episode of Science Break.